Okay, so we're going to go over exercise 3, and this whole packet you're going to use as your notes for this unit. This, your reading guide, and the video sheet that we're doing later today, that's going to be what you study when we take this test. All right, you're going to want to use your highlighter on some of these definitions. Okay, so it says, in Thailand, water plants such as lily pads are a daily problem for citizens. Since cities are built around waterways, people often commute using boats and ferries instead of cars. The outboard engines are frequently getting clogged with lily pads, which grow quickly and are hard to eliminate. Okay, the rate at which the lily pads started to grow very fast after several days. Okay, if you want to keep any part of your pond clear, you will have to cut out more than half of the lily pads every day. And what that represents, what you constructed represents exponential growth. Okay, highlight this part here. Okay, exponential growth occurs when there are no limits to the size at which a population can grow. Okay, so we have exponential growth when there's nothing limiting the size of the population. So what do populations need to grow exponentially? What would the lily pads need to be able to grow forever? What do they need? Okay, they need space. What else? They need water. Okay, you're close. They don't need food because they can do photosynthesis, but they need sunlight. Okay, and they're also going to need some nutrients that they're going to get from the soil that they're in. Remember, plants make carbohydrates, but they still need nitrogen and phosphorus, and they get that from the soil. Okay, they get that from the soil, so they're going to need those nutrients. Those are things that would need to grow forever, but which of these will eventually limit the lily pad's growth? Okay, space and indirectly sun. So which of these will eventually limit? That's going to be the space, and the reason it limits it is because they can't grow on top of each other. If they do, they'll run out of sunlight. So it's space and sunlight that are going to limit the population size of the lily pads. Okay, today we're going to introduce 2 new terms for this unit that you need. We learned about exponential growth, and you graphed exponential growth in our last class. Today, you're going to learn about carrying capacity and what limiting factors are. So I want you to come in, we're going to read this, and we're going to highlight our definition. There is a maximum number of lily pads that can grow in your pond. Okay, there's also a maximum number of organisms that can live in an ecosystem, and that is carrying capacity. Okay, it's the maximum number. Okay, in this case of lily pads, but of any organism, okay, in an ecosystem, there's a max number. Okay, factors can limit what an ecosystem can carry. There are several factors that limit the carrying capacity, and they are called limiting factors. Okay, so those are things that we just talked about: climate, food, water, sunlight. When you run out of those things, that's when you've reached your carrying capacity. Have you guys ever seen, like in a restaurant, it'll say like 150 capacity, like it'll say maximum capacity, and then it'll have the number of people that can be in that restaurant? Or if you go on an elevator, it'll say weight capacity. That's the most weight that elevator can hold. Or when you're crossing a bridge, sometimes the bridge will have a maximum capacity. Capacity is just how much can be held, okay? And when we're talking about carrying capacity, it's how many organisms can be kept in that ecosystem. Okay, your carrying capacity on this graph, is right here. Okay, so this graph is showing what it looks like when populations stop growing. It's called logistic growth, but it's also called the S-curve. That's even harder than the J because it's really hard to see the S there, but it's called an S-curve sometimes. You can kind of see it. All right. So this point when it levels off, we're going to go ahead and label it, and then we'll answer the questions. The point where this levels off is called the carrying capacity. So that's the max number of organisms this ecosystem can hold. And you can see that it oscillates Oscillates means it goes up and down. That's the part of it that's logistic or logarithmic. It's oscillating up and down. And what's causing that is changes in the season. And we'll get to that in a minute. But ecosystems don't have the same amount of resources all year long. It changes. So that's what that oscillating is. Look right here. This should look an awful lot like your last graph. Do you see how every population starts out as a J? Every population starts out growing exponentially. This is the exponential growth phase. Right, so this is how most populations grow. They'll grow exponentially until they reach carrying capacity. So you need to be able to find on a graph the exponential part where they're doubling, okay? And you need to be able to find where it levels off. Okay, so is this a population growing with or without limiting factors? With limiting factors, okay? It's your limiting factors that are causing this population to stay low. Okay, these are limiting factors that are forcing this population down. And again, it could be things like food or water or space that are keeping that population from growing too large. So we've labeled the parts on the graph, and now we just need to answer our questions. What is the carrying capacity in this graph? It's 500. Okay, you've got that little dotted line that shows you what the average of those oscillations, the up and downs are. Okay, it's the 500. Okay, sometimes you won't have that up and down, and it'll just look like this. Okay, and you'll just have to find the spot like that where it levels off. Okay, it'll always be easy to find. It's going to be where the graph levels off. Okay, a majority of populations begin to grow exponentially, and then as resources become limited, they reach a carrying capacity. What part of the graph represents the original growth, the exponential growth? A or B? A. Okay, so this is A. That's the exponential growth phase. We've already labeled it. And then number 3, what seasonal factors could account for the oscillation, the regular increase and decrease of the population around the carrying capacity? What could change seasonally? What changes between winter and spring? There's a bunch of things. The plants that are available. Okay, so that could be like the food availability. And then what else? Okay, the weather, temperatures. Okay, there may be some especially like with insects, there might be some temperatures that are so cold the population can't survive that temperature. Even if there's babies being born, they're not living. Okay, rainfall can change. And the other thing that changes seasonally is predator-prey relationships, and we'll talk about that more in the next unit. But one thing that can cause a population to oscillate like that forever is predator-prey. Think about it. If you've got, we're about to watch a little video clip that talks about mosquitoes and bats just a little bit. Okay, if your mosquito population gets really big, what's that going to do to the number of bats? They're going to increase too because they have more food, right? Well, they're going to increase so much that it's going to do what to the mosquito population? It's going to bring it back down, right? And then when the mosquito population comes back down, what's going to happen to the bat population? It's going to go back down too. And it'll just go on like that forever and ever. They'll kind of check each other's population. One will increase, the bats will follow, the mosquitoes go down, the bats go down. Predator and prey can oscillate like this, like you saw, okay, for a long, long time, forever, infinity. Okay, so that's food availability, or predators too. Number 4 is just a throwback to yesterday. I don't know if you guys remember. What is the carrying capacity for the lily pad population? If half the capacity was 512, then the total capacity was what? 1,024. Okay, and that is it on this sheet, but we need to learn a little bit more about limiting factors. And I've got a video that I want to show you to help us with that. I'll stop it in several places. It's on the front page of Schoology.
In our series on biology, we spent many weeks together talking about the physiology of animals and plants and how cells work together to make tissues, to make organ systems, to make us the hunks of meat and vegetables that we are. In understanding the whole organism, it's important to know what's going on at all those levels. And the same is true for ecology. Only instead of zooming in and out on different levels within a living thing, we can zoom in and out on the Earth. Depending on the power of the magnification, we can understand a whole range of things about our planet. For instance, we can look at groups within a species and how they live together in one geographic area. That's population ecology. There's also community ecology, where you look at groups of different organisms living together and figure out how they influence each other. And then the most zoomed out we get is ecosystem ecology, the study of how all living and non-living things interact within an entire ecosystem. So let's start by zooming in with population ecology, the study of groups within a species that interact mostly with each other, to understand why these populations are different in one time and place than they are in another. How? You may be asking yourself, is that in any way useful to anyone ever? Well, it's actually super useful to everybody always. Let's look, for instance, at the outbreak of West Nile virus that struck Dallas, Texas in the summer of 2012. In Dallas County, 12 people died from the virus as of the filming of this, and nearly 300 people have been infected. But in 2011, the whole state of Texas reported only 27 cases of West Nile and only 2 deaths. That seems kind of significant. So what's up? Turns out that this is a population ecology problem. West Nile is a mosquito-borne illness, and the population of mosquitoes in Dallas in 2012 busted through brick walls like the Kool-Aid man, spreading West Nile like crazy. So why did this outbreak happen in 2012 and not the year before? And why did it happen in Texas and not in New Jersey? The answer is population ecology.
So if you're at home, make sure that you've pulled up the population ecology crash course worksheet on the front page of Schoology and write down the relationship on number 1 between mosquitoes and West Nile. Mosquitoes carry the West Nile virus.
Before we start solving any disease outbreak mysteries, we gotta understand the fundamentals of population ecology. For starters, a population is just a group of individuals of one species who interact regularly. How often organisms interact have a lot to do with geography. You're going to have a lot more face time with the folks you live near than those who live farther away. As a result, individuals who are closer to you will be the ones that you compete with for food and living space, mates, all that stuff. But in order to understand why populations are different from time to time and place to place, a population ecologist needs to know a few things about a population, like its density. In this instance, how many mosquitoes there are in the greater Dallas area that might come into contact with each other. A population's density changes due to a number of factors, all of which are pretty intuitive. It increases when new individuals are either born or immigrate, that is, move in, and it decreases because of deaths or emigration, or individuals moving out. Simple enough, but as a population ecologist, you also need to know about the geographic arrangement of the individuals within the population. This is their dispersion. Like, are the mosquitoes all clumped together? Are they evenly spaced across the county? Is there some kind of random spacing? The answer to these questions gives scientists a snapshot of a population at any given moment. And to figure out a puzzle like the West Nile outbreak, which involves studying how a population has changed over time, you have to investigate one of population ecology's central principles: population growth. There are all kinds of factors that drive population growth, and they can vary radically from one organism to the next. Things like fecundity, how many offspring an individual can have in a lifetime, make a huge difference in the size of a population. So for instance, why do mosquito populations seem to grow so quickly, while the endangered black rhino may never recover from a single act of poaching? For starters, mosquitoes can have 2,000 offspring in their 2-week lifetime, while the rhino can have like 5 in 40 years. Still, a population doesn't usually or even ever grow to its full potential, and it can't keep growing indefinitely.
Okay, that was your answer to number 2, fecundity. It's a measure of how many and how often an organism can reproduce, how many offspring they can have in a given amount of time. And it's not just about the number of organisms produced, but how often. And a lot of times we do see smaller organisms like insects and microorganisms like bacteria being able to reproduce in this way. And that can have implications because it's those smaller organisms that
can often carry disease like bacteria and like the mosquito. Not all of those organisms cause disease, but those that do are able to reproduce quickly, spreading disease quickly. If you look at larger organisms, and in particular mammals like the rhino, the elephant, even humans, we have less offspring less often, so our fecundity is much lower. Think about humans, for example. Our maximum fecundity would be like one offspring every year on average for most women. So fecundity makes a difference in how quickly a population can grow.
Definitely. To understand how fast or slow and high or low a population actually grows, you need to focus on what's keeping growth in check. These factors are appropriately called limiting factors. Say you're a mosquito in Dallas in 2011, the year before the outbreak. Back then, the growth rate wasn't what it was in 2012, so something was keeping you down. To figure out what your limiting factors were, you first have to narrow down what you need as a mosquito to live and reproduce successfully. First, you gotta find your food. Now, you mosquitoes, you eat all kinds of things, but in order to reproduce, assuming you're a female, you need a blood meal. So you have to find a vertebrate and suck some of its blood out. Presumably, there's no shortage of vertebrates walking around Dallas for you to suck blood out of. I have good friends who are vertebrates in Dallas. You might even be able to suck some of their blood. Next, temperature. Because you mosquitoes are ectothermic, it has to be warm in order for you to be active. And Texas is pretty warm, and the winter of 2011-2012 was especially balmy. In fact, the summer of 2012 was exceptionally hot, which helps speed up the mosquito life cycle. So that's one limiting factor that's been removed for Dallas area mosquitoes. Moving on to mates. If you're a female mosquito, you need to find a nice male mosquito with a job and preferably his own car, because you know Dallas is pretty big city to mate with. This isn't actually all that hard because of the way that mosquitoes do it. Males just gather into a mosquito cloud at dusk every night during mating season, and all the female has to do is find her local dude cloud and fly into it in order to get mated with. Easy cheese. Finally, space. And aha, because here we have another important clue. Mosquitoes need to lay their eggs in stagnant water, and if there's anything mosquito larvae hate, it's a rainstorm flushing out the little puddle of water they've been living in. And since Dallas saw a pretty severe drought in the summer of 2012, there were lots of pockets of stagnant, nasty mosquito water sitting around, acting as nurseries for many, many West Nile infected mosquitoes. So when we look at this evidence, we find at least two limiting factors for Dallas's mosquito population growth that were removed in 2011. The constraints of temperature and space. It was plenty hot, and there were lots of egg-laying locations, so the bugs were free to go nuts. Population ecologists group limiting factors like these into two different categories: density dependent and density independent. They do it this way because we need to know whether a population's growth rate is being controlled by how many individuals are in it, or whether it's being controlled by something else. And the reason these limitations matter is because they affect what's known as the carrying capacity of the mosquito's habitat. That's the number of individuals that a habitat can sustain with the resources that it has available. So, density-dependent limitations are factors that inhibit growth because of the environmental stress caused by a population size.
Guys, I know he spoke way too fast for you to get that definition. Just write down examples as you listen on the next two questions of density independent and dependent, and we will write the definitions down after the video.
For example, there may simply not be enough food, water, and space to accommodate everyone. Or maybe because there are so many individuals, a nearby predator population explodes, which helps keep the population in check. Things like disease can also be a density-dependent limitation. Lots of individuals living in close quarters can make infection spread like crazy. Now, I don't think that the Dallas mosquitoes are going to run out of vertebrates to dine on anytime soon, but let's say hypothetically that the explosion of local mosquito populations caused a similar explosion in the number of Mexican free-tailed bats, the official flying mammal of the state of Texas. And they eat mosquitoes. That would be a limiting factor that was density dependent. More mosquitoes leads to more bats, which leads to fewer mosquitoes. It's pretty simple. When density dependent limitations start to kick in and start to limit a population's growth, that means that the habitat's carrying capacity has been reached. But the other type of limiting factor, the density independent ones, have nothing to do with how many individuals there are or how dense the population is. A lot of times these limitations are described in terms of some catastrophe, a volcanic eruption, a monsoon, a Chernobyl. In any case, some crucial aspect of the population population's lifestyle changes enough that it makes it harder to get by. But these factors don't have to be super dramatic. Going back to mosquitoes, say in 2013, there's a huge thunderstorm, a real gully washer in Dallas every day for 3 months. That's going to disturb the clutches of mosquito eggs hanging out in the stagnant water, so the number born that year would be substantially smaller. By the same token, if the temperature swung the other way and it was unseasonably cold all summer, the bug's growth rate would drop. Now, the truth is, there are 1.5 billion situations, both big and small, that could lead to a population either reaching its carrying capacity or collapsing because of external factors. It's a population ecologist's job to figure out what those factors are. And that is what math is for. Our friend math says that any population of anything will grow exponentially unless there's some reason that it can't. Exponential growth means that the population grows at a rate proportional to the size of the population. So here at the beginning of 2012, we might only have had 1,000 mosquitoes in Dallas, but then, after say 1 month, we got 3,000. Now with 3 times as many reproducing mosquitoes, the population grew 3 times as fast as when there were 1,000. So then there are 9,000, at which point it's growing 3 times as fast as when there were 3,000, and on into infinity. And in this scenario, the mosquitoes are all carrying capacity, my chitin covered butt. There's no stopping us. But you know what doesn't really happen? I mean, it can happen for a while. Humans have been on an exponential growth curve since the Industrial Revolution, for example. But eventually, something always knocks the population size back down. That thing might be a density-dependent factor like food scarcity or an epidemic, or a density-independent one like an asteroid that takes out the whole continent. Regardless, this exponential growth curve can't go up forever. And when those factors come into play, a population experiences only logistic growth. This means that the population is limited to the carrying capacity of its habitat, which, when you think about it, ain't too much to ask. See how this graph flattens up at the top? The factor that creates that plateau is almost always a density-dependent limitation. As you add mosquitoes, eventually the rate of population growth is going to slow down because they run out of food or space. And when we get to where that number levels off, that number is the carrying capacity of the mosquito population in that particular habitat. Now, let's apply all of these ideas using a simple equation that will allow us to calculate the population growth of anything we feel like. I know it's math, but wake up, because this is important. The city of Dallas is depending on you. So, let's calculate the growth of Dallas's mosquito population over a span of 2 weeks. All we have to do to get the rate of growth, that's R, is take the number of births minus the number of deaths, and then divide that all by the initial population size, which we generally just call N. So let's say we start with an initial population of 100 mosquitoes, and each of those mosquitoes lives an average of 2 weeks, so our deaths over a span of 2 weeks will be 100. Half of these mosquitoes are going to be female, so 50 of them, and they can produce about 2,000 babies in their lifetime, so that's times 2,000. Ooh. So 50 mommy mosquitoes times 2,000 babies per mommy, and you get births equaling 100,000 little baby mosquitoes. Once we plug in all the numbers into this equation, even though this is totally a hypothetical, we will see the true scope of Dallas's mosquito problem. So blink, in 2 weeks the population had 100,000 babies and only 100 of them died. So this is a population growth rate, if you do the math, of 999. This means that for every mosquito out there at the beginning of 2 weeks, there will be 999 more at the end of 2 weeks. That is a 99,800% increase by Thor's hammer. Again, these are hypothetical numbers, but it gives you a sense of how a population can just go out of control when all the factors that we talk about go in its favor. And you guys haven't even seen trouble until you see what the graph of human population looks like over the last couple of millennia.
Okay, so now let's go back and give our definitions for number 5 and 6. Unfortunately, my voice on this did not save when I was switching my mic back and forth, so I'm going to come in and voice over what I wrote to the class. On number 5, your definition for density dependent limiting factors. The first thing that you need to know, it's not really the definition, but it's the most important thing to remember, is that population size does matter. And this definition would probably be a little bit easier to remember if it was population size dependent limiting factors. But the reason it refers to density is, remember that we define a population as living in a certain geographical area. So in that area, as the population size increases, so does the density. Think about the population of Woodruff versus the population of Columbia. Yes, Columbia is geographically bigger, but there's also more people in the space. The density is greater. So as population size increases, so does density. Okay, for our definition, these are factors that increase in effect as the population size increases. In other words, these are factors that will be more limiting on the population as the population size grows. And you should have recorded some of those examples during the video. These include things like food, water, and space. And again, you recorded some examples from the video, but two factors that I want you to make sure that you have written down as density dependent are disease and predators, because these two are probably our most missed density dependent factors. With disease, this is what we're dealing with right now. This is why we're trying to say 6 feet apart and wear masks. When you're in closer contact with members of your population, you're more likely to contract and spread disease. And as that disease spread, it's going to limit the size of your population. It's going to decrease the size of your population. And then with predators, we talked about that a little bit earlier. As your population grows, there's going to be more predators attracted to your area or growing in your area. And eventually that is going to have a big limiting effect on your population. So disease and predators are the two most missed examples of density dependent that I want you to remember. Okay, now let's come in and write our definition for number 6. For me, this is the most difficult concept to understand in this unit. Density independent limiting factors. And these are limiting factors where size does not matter. Okay, population size does not matter. It's going to affect all members of the population regardless of size. So it will have the same effect regardless of if it's acting on a small population or a large population. And as he mentions in the video, a lot of times density independent factors will be described as a large natural disaster. So like a forest fire, a hurricane, a tornado, but it doesn't always have to be that extreme. It can be something like weather. An example of weather, a few years ago, up in Hendersonville in that area, in the apple orchards, there was an unseasonable frost. So I can't remember if it was an early frost or a late frost, but there was an unexpected frost and it killed the majority of crops in that area. And so it didn't matter if you had a farmer with 15 apple trees or 1,500 apple trees, they were all affected by that frost. The weather created an unseasonable limiting factor that affected all the apple trees in that population. So weather is a big one. Unseasonably hot or cold seasons. It can be extreme drought or extreme rainfall. Those are examples of weather. Natural disasters, hurricanes, tornadoes, mudslides can wipe out an entire plant population, for example, regardless of the size. And then the last one is human activities. When we come in and we clear out areas, for example, if I want to clear out, like a forest to build an apartment complex, it doesn't matter how many organisms are living in that area, all those populations are going to lose their living space. So those are your 3 for density: independent, weather, which can include temperature changes and changes in precipitation, natural disasters, and human activities. Those are your density independent factors. You've got to remember, it doesn't matter how many individuals are in the population. It's going to have the same effect regardless of population size. Okay, and now if you'll look at your last question, I believe it's number 8. Please go in and record your answer to number 8 based on what we've talked about, and then submit that on Schoology for me, and I'll give you feedback on your answers. Thanks, guys.